So last class we looked at how to do tracking compensation, right? We thought about initially started off adding a resistor, maybe 2 classes ago. Started off adding a resistor. Then we found that, you know, by moving the resistor around, we can actually come back and cancel the second pole, right? So then, what we did is we wanted to find a way to actually make these two track so that you have perfect cancellation. And the first method we looked at was to implement this resistor using a MOSFET. Okay? And what we did is we implemented it using a MOSFET, and then we also biased it such that it actually tracks the GM, such that the GDS of this MOSFET, which is the RF, would track GM6. Correct? Everybody remembers that? So that was the first method. First method of tracking compensation was to use a MOSFET. The second method we looked at today uses a real resistor. Okay? And what we are going to do is we are just going to use RF as we started off with, but now we are going to generate a GM6 which is going to track RF. Okay? So let me quickly draw the two-stage op-amp. So this is your two-stage op-amp with your zero cancelling compensation. So now what we are going to do is we are going to bias this using a circuit which is going to create a current, okay, such that GM6 tracks RF. Okay, so let's look at what it's actually a fairly simple circuit. You may have seen this before. I'm going to call this resistor RB. And these transistors MA, MB, MC and MD. Okay. This is some bias current IB. MA to MB ratio is 1:1. This MC to MD ratio is some 1:n. Okay. So this is your bias generator. So this portion is often called a K prime generator or constant GM. So this is often called a K prime generator or a constant GM reference. Okay. So first of all, you can see that, okay, so the current, because of this mirror, the current in the two branches has to be equal. You first of all assume that all four of them are in saturation. Okay, that is obviously a good starting assumption. And then, because you have a mirror here, these two currents are equal, both branch currents are IB. In that case, you can actually write an equation across MC, MD, gates and sources, right? So if you do that, Okay. So VSGC has to be VSGD plus IBRB. So which means the overdrive voltage, which is VGS minus VT, VDSAT, whatever you want to call it. Okay. So this is one relation between the VDSATs of the two devices. What do we know? We also know W over L D is N times W over L C, and IB is the same current which flows through both these devices, right? So we also know one more relation between the overdrives. Right? We know this. Correct? Okay? Which means V overdrive C is V overdrive C over N root N plus IBRB. You can rewrite the original equation. Now you can write your V overdrive in terms of multiple things. We will write it in terms of the GM. Okay, you will see why it's called a constant GM reference. This is 2IB over GMC. Okay. Plus IBRB. Okay. So first of all, IB equals 0 is a valid steady state for this circuit, right? If IB equals 0, the VGSs are 0, so the drop across RB is also 0, so it will satisfy all the equations. So most probably for this kind of circuit you will need a startup, some kind of startup circuit, okay, which brings it close to your final steady state, and let's go after that. Is that clear to everyone? Yes? Okay. First of all, if all currents are 0 inside this, right, is that a valid steady state? Inside this portion. What do the MOSFETs need to satisfy? They need to satisfy their current voltage relationships, right? If all currents are 0, will it satisfy the current voltage relationship? It will. It definitely will. For yeah, of course. No, naturally, yeah. I'm assuming RDS is very large. Okay, of course. I'm already assuming RDS is very large. Okay. So now what we are going to do is, if IB is not 0, then we cancel out IB throughout. Okay. So you get a relationship between GMC and RB and root N. Okay. And now you know GMC in terms of the current IB, and you can solve for IB. Okay. The same thing. This is your GMC. So IB gives you KP, sorry. C and D are the PMOSs, so it's KP. you'll get something like this. Okay, something. So in other words, your IB is proportional to 1 over RB squared. Okay. Right? And now let's say the same IB is mirrored into, so let us say this is, let me number these guys, M2, I'll call this M7. So the same IB is being mirrored into M5 and M7. Okay. So now if that is the case, if the bias current is proportional to 1 over RB squared, what will the GM of 6 be proportional to? 1 over RB, because GM is related to root of the current. Correct? In which case, you can, if you make the same type of resistor, if you make RB and RF the same type of resistors, and you choose RB such that GM6 is 1 over RF, then you can make sure they cancel out. Correct? Is that clear? Oh, sorry. So of course RB and RF have to be the same type of resistance, and it will track over temperature, process, everything. Okay? So what we needed was RF equals, right, this is the value we needed to cancel out the pole, the second pole. Right? Sorry, did I say, yeah, I think maybe earlier I said GM6 needs to be 1 over RF, that's wrong. RF needs to be 1 over GM6 times 1 plus CL over CF. This is for cancelling the pole. If you make GM equals 1 over GM6 equals RF, that will push the pole to infinity. Right? Okay. Okay? So, okay, so this is the other kind. Okay, so that's it. We are done with tracking compensation. Is that clear to everyone? How you generate this current, bias current? Yes. Yes, it will, but that's okay. I mean, that's not a big problem. The way I did that, because we just there are multiple reasons. One reason, of course, is that for your one of the conditions we got was that GM1 and GM6 are related, because you may want to push there are certain conditions, right, about wanting to push the zero out very far, first of all, right? You start off with that condition. For that condition, GM6 needs to be much larger than GM1, and you want that also to track with process and temperature. Okay? So you would first design such that the zero is very far out, then try to cancel it, because in case you have a pole zero doublet, at least the pole zero doublet at least will be outside the omega u. Yeah, we are changing the bias current. The bias current and the differential pair will depend on RB. That's all. I'm not changing it. With process or temperature, right? RB will change with process or temperature. You are changing the bias current, but I mean that's fine. That's not a major problem. Of course, if you don't want to do that, then you'll need to generate it completely separately. That's all. Yes. RB and RF can have, of course, you can have random mismatches, right? This will take care of systematic mismatches. This will take care of temperature variations, for example, right? And so you can, at the end of the day, you can match it to within maybe 0.1% or something like that, right? Beyond that, you can't do much. Okay. Okay. So what we'll do is we'll do a quick design example. So the design example I'll do in class will just be a simple pole splitting compensation without the zero. Okay. You'll be doing it for the project. Okay. The pole splitting one. Okay, so I'll give you the specs. So we'll do it very similarly to what we did for the telescopic. So I'll give you all the relevant specs. So I'll say this is greater than or equal to 80 dB. Okay, 80 dB means it's 10,000. Okay. I'm going to give you a spec saying the unity gain frequency is greater than or equal to 5 megahertz. Output peak to peak voltage swing is larger than 4 volts. Phase margin is greater than 60 degrees. And finally slew rate is greater than or equal to 10 volt per microsecond. Okay, these will be your design specs. So let us say I ask you to design such an op-amp. Okay, and of course I'll give you the usual things. I'll tell you VDD is 5 volts. Let's say these are slightly different from what we had before. Okay, then I'll tell you L minimum is 2 microns. Then I'll give you something slightly different. So let us say for the L minimum I'll give you lambda L itself instead of giving you lambda directly. I think class in the telescopic op-amp case I gave you lambda for L min, right? I'm just giving you lambda L for L min. Okay? Suppose I give you all of these. So this is what you're asked to design for. How would you proceed? What would you start with? What are the differences first of all with the previous case, with the telescopic op-amp case? Yeah, you said that, sorry. Yeah, power consumption, right? So that is one difference. I have actually not given you the power consumption spec. Okay, what else? I have given you the slew rate, I have given you the phase margin and the unity gain frequency. Okay, how would you start off? How did we start off the previous case? In the case of the telescopic op-amp, we started off with the power consumption and decided the bias currents. Okay, it seems like that is the easiest way to go because once you design bias currents, there are a lot of things which get clarified. So how do you decide the bias currents here? Slew rate, right? We noticed that for the single stage op-amp, the slew rate is intimately connected with your bias current. But in that case, there was just a single stage. In this case, what happens? Okay, so let me do one thing. I'm just going to copy this portion. It's okay. Okay. Okay, so we decided that we want to start off with the slew rate. What is the slew rate of this op amp? So let us say, let me call this VO. What is the slew rate of this op amp? So I think I use CC for the simple case, right? And let me call this current IA. I'm going to call this current IB. These are the two bias currents, IA and IB. Okay, so yes, so that is an important point. Load capacitance is 10 picofarad. So what is the slew rate of this? IA by CC. Why is that? IB by CC? So you have two currents and two capacitors, right? One of them has to be IB by C. Which one of them means there is only a single slew rate, right? There is a slew rate, you have two specs. One is positive slew rate, other is negative slew rate, right? Okay. So let us say, okay, do you want to consider the positive or the negative one? Well, what do you do when you need to do slew rate, when you need to measure the slew rate? What is the definition? You need to apply a very large step at the input, right? So instead of a small signal, you're going to apply a very large step on one side, very small step on the, very low, zero voltage on the other side, let's say, 0 on VDD, for example. Correct? So what happens in this case? So let us say VI2 was VDD, VI1 was 0. What happens? IA flows through M2. What is the current in M1 and M3? 0. What is the current in M4? It has to be 0, right? If M3 current is 0, the gate to source voltage of that is 0, M4 is 0. Correct? Okay. So all that current IA flows through CC. Okay. So what is your output slew rate? We'll make one more assumption. We know that we want to push out, well, it's not an assumption, it's a very valid assumption because we have talked about this before. We want to make GM6 much larger than GM12. We already know that because you want to push out the 0 very far, right? Much farther out of the unity gain frequency. What is the unity gain frequency of this op amp? GM1 by CC, right? What is the 0? GM6 by CC, right? So you already know you want the 0 to be much farther out for good phase margin, much farther out than omega u. GM6 is going to be very large compared to GM1, which means, let me call this voltage Vx. Vx is probably going to be very small for any signal, whether it's small or large. If I'm applying a signal at the input, right, it is going to look like a virtual ground because GM6 is very large. Okay, so you can assume that IA which flows through CC creates a voltage V out, and you can write a direct relationship. dV out by dt is nothing but IA over CC. So this is the condition we know. So Vx looks like a virtual ground, right? You know, you have studied the concept of virtual ground before, right? If you have a very large gain, you have a virtual ground at the input, right? Okay, so Vx looks like a virtual ground, correct? Which means, let me use red color here. So IA current flows like this through CC, And you can now write a relationship between V out and IA and CC, because it's just a DC current charging a capacitor. Okay. Now, here we are assuming that IB is large enough to not limit, right? Because now IB also needs to charge, for example, CC, there are actually CL, there are other constraints here. We'll start off by assuming that the slew rate is input limited. Okay, in this case, you can have input limited slew rate and you can have output limited slew rate. Okay, in the case of the two-stage op-amp, there are actually lots of caveats. You have to be very careful. If IB is large enough to not affect the slew rate, then slew rate is IA over CC. Okay, the other condition is now M6 needs to be able to source not only IA. So how will M6 now, all of this current actually flows out from M6, right? Which means M6 needs to be large enough and the voltage at Vx needs to be small enough such that such a large current can flow through IB plus IA plus whatever is, right? All of that needs to flow through M6. Okay, so that is one condition, but this assumes that input slew rate is input limited. Okay, what if the input step was the other way? Let's say this was very large, this is very small. What will happen? What is current through M2? IA will all flow through M1 and M3. That will flow out through M4 and then it is charged, so this will be the opposite slope, right? One will be the positive slew rate, other will be negative slew rate. Okay, so if it is input slew rate limited, it will be IA by CC in both cases, right? Okay, what do you do if you want to make sure it's not output limited? So let us say output current was limiting the slew rate. Where does IB flow through? CL. It actually also flows through CC because now you have a Vx here, right? If this was limiting the slew rate, if IB was limiting the slew rate, right, then it would need to source current through both of these. So now you can say IB needs to, so your slew rate limited based on the output is IB over CC plus CL. Okay. Based on these two conditions, you can actually find out IA and IB, because once you are given slew rate needs to be much larger than a certain value, a certain spec, right? You can calculate the values of IA and IB. Okay, so let us say so now we want to calculate IA and IB. We know CL, what about CC? Right, we know the slew rate, we decided we want to calculate the current from the slew rate, but looks like we need the value of CC. How do you calculate CC? From the phase margin, right? If phase margin is 60 degrees, right, you can calculate CC. I give you the answer now, but I want you to go back and try to calculate, in this case for 60 degrees. In class we saw what happens if you have 45 degrees, right? If you have 45 degrees, you want the second pole to be right on omega u. If you want 60 degrees, it will be a new calculation. What you will find is you will see that CC needs to be greater than, of course there is an inequality here, needs to be greater than or equal to okay, you get something like this. And we all, of course, so now this is not a perfect relationship because now you have GM1 and GM6, but now we also know GM6 needs to be much larger than GM1. We can put in a certain number, You can say I want it to be 10 times. So let us say you want your 0 to not have any effect on your phase margin. Okay, then you put a condition saying the 0 should be 10 times omega u. Okay, if you say 0 is 10 times omega u, it will tell you GM6 is 10 times of GM1. Everybody remembers this? Okay, so in other words, from this I am going to say I am going to choose a value. Okay, it just needs to be greater than or equal to. Right, in this case if you choose 1/10, you will say 0.22 times CL. I am going to choose 0.25 times CL. What we have to do is, let us say you choose this number, you have to go back later and there will be certain checks you have to do. Right, we will go through that also. Right, once we finish the design. But let's choose CC equals 0.25 times CL. Okay, what is this? 2.5 picofarad. Correct? Is everything clear so far to everyone? Okay. Okay, so from this you get you get 25 microamps. Yes. So the thing is, because you have two sets of bias currents, you have an input stage bias current and an output stage bias current, right? Depending on that, depending on the values of each of these, you will have a certain limitation on the slew rate. We saw the case, for example, when if output slew bias current is very large, then it will end up that, I mean, you'll reach a state where your slew rate will be completely limited by your input stage only. Okay, which will be the case IA by CC, because IA needs to charge up the CC. Okay, if you assume that IB is very small, then you need to say IB needs to charge CC plus CL to generate this voltage V0. Okay, which means it's limited by the bias current of the output stage. That's why I say input and output limited. Okay. No, that is not necessarily true, because if one is very much larger than the other, then it is not the case, right? If IB is large enough to not limit it, then it would never come into the equation. So you can't say that it's the sum of the two. Okay, what you can arrive at are the minimum conditions such that it doesn't limit it. Right? That's all you can arrive at. Yes. Of course, right? In fact, what you'll see is, what we'll use this to is arrive at a first cut relation, right? At any time when you do a hand calculation, you do a first cut relation, then you'll have to go back and check your assumptions, right? So what I'm going to do is, I'm going to choose IA and IB based assuming that they perfectly limit the slew rate, right? Then you'll have to go back, either do more detailed calculations, more detailed analysis, or run it through a simulator, because there are other non-idealities you have to take into account anyways, right? You could put it into a simulator and see if it is good enough. Okay, one of those two things you have to do. So this one gives you, input limitation gives you IA is 25 microamps. So we'll just choose IA as 25 microamps. Okay, that's a good starting point. Okay, so IA is 25 microamps, IB is 125 microamps. So now, so far, you have actually, you have actually taken into account two of the specs, which is the phase margin and the slew rate. And you have got your bias current and CC. What do you find out next? unity gain bandwidth, you can find out GM1. Okay, that is another thing you can do. Okay. So again, we always deal with inequalities. Remember that GM1 by CC is omega u, not FU, right? The unity gain frequency is given in megahertz. Sorry. So the GM1 needs to be larger than 78.5 microsiemens. Right? 2.5, 5e6 and 2.5, that ends up being 78.5. Okay? Everything clear so far? So from this what do you find? W by L of 1. Can somebody calculate it and tell me what it is? By the way, when I say somebody, everybody plays. Right? Sorry? You want me to go here for the... You're getting around 5. Yeah. You must be getting like 4.9 or something, right? Okay. So it ends up being something like 4.9. Did everybody get that? Okay, yeah. These are the parameters we have. You're getting 4.9? Okay. Okay, so it ends up being 4.9. So we'll assume like 5, right? That's a good enough assumption. Okay. So now you have set up WRL of, you have found out WRL of 1 and 2. Okay, what next? What next? From swing limits, right? That's what we did for the telescopic op-amp. We'll do exactly the same here. From the swing limits, we'll find out WRL of the output stage. Correct? We'll come to M3, M4, right? M3, M4, it's not so directly obvious how to design those. Why is that? Where does it, with WRL of M3, M4 figure, No, yeah. For the output stage, that's okay. What I'm asking is, so he had a question about M3, M4, right? He's asking about these two guys. Does the W over L of those things matter? Of these two devices, does it matter? Does it figure anywhere? Gain. How does it figure into the gain? What is the gain of the first stage? It's GM1 over GDS2 plus GDS4. So W over L doesn't directly figure into it. L figures into it, but not W over L. Anywhere else? Huh? Swing limits. Why? We already figured out that GM1 is much more than GM6. Most of your gain is coming from GM6. So you don't have a very large swing here. Right? Exactly. It's going to affect your input common mode range. We have not given that spec here, but you still have to calculate it. Correct? Because the VGS of this is going to decide how high your input common mode can go. Okay? But we'll come to that at the end. So what we'll start off doing is, it's a good enough assumption to start off assuming that these guys have the same VDSAT as the others. We'll start off like that, find out the input common mode range. If at all there is a spec, we'll find out if it's limiting it in any way. Okay? So we want, we want 4 volts peak to peak. So what does it tell us about the VDSAT? So what is the condition if you want output to be 4 volts peak to peak? The supply is 5 volts, the other end is ground. So the simplest way to distribute it is 0.5 for M7, 0.5 for M6. Correct? Okay, you're right. What you'll have to do is, so far we have not fixed GM6 per se. We have actually fixed GM1. We have assumed that GM6 is much, let's say more than 10 times GM1. Okay, what you'll have to do is find out GM6, find out W over L6 for meeting the VDSAT condition. Okay, and then find out if it meets your GM6 much less than, greater than 10 times GM1. You could do it that way. Or like you said, you can assume it's 10 times, see if it meets the VDSAT condition. One of those two things you have to do. Right? We'll do it this way. Okay, we'll just start off with VDSAT, see if it meets the condition. So we are going to say both sides have 0.5 volts. So based on this, IB, right? You can find out W over L of each one of these guys. Okay? So I'll give you the values. I want you to go back and check it. Okay? So you say, we find out that this guy has W over L of 20. What will this be? If this has a W over L of 20, what is W over L of 6 going to be? Right, 40. Why? Because mu and Cox and mu p Cox are related by a factor of 2. Right? One is a PMOS, other is NMOS. They have the same bias current. Mu and Cox is 2 times mu p Cox. VDSATs we are designing to be the same. W over L of the PMOS has to be double that of the NMOS. Okay? Again, you can find out now that you have assumed this is VDSAT, you can decide M5, and let's say if you had a some IREF here. I'll call this M8. So now this you have designed for a VD sat of 0.5. So of course this is a current mirror. So all of these guys have to have the same VD sat. Correct? Isn't that right? For a current mirror. Okay. So which means once you know IREF, if you say we can pick out a number, let's say 100 microamps, right? You can pick any number you want. Then you know M8, you know M5. So there you know the VD sat, you know the currents. M5 contains, carries 25 microamps. Correct? Is that clear? You can get these two. Correct.
But if we do the constraint on GM and we get a larger value of W over L, then our VD sets will actually be lower. So
yes.
it always lead to a lesser constraint on GM. If we aren't given any, it doesn't matter how big we make the transistor because we aren't given any constraint about capacitance.
Correct. So actually we haven't come there so far. You're right. So that is one of the checks you're going to do. Did you calculate it out? Correct. In fact, we are going to come to that. So it turns out that GM6 happens to be only some 6.3 times, 6 times. So some 6 times GM1, right? It so happens that means that you need to increase W over L of 6 anyways. Is that the only way to do it? Yeah, you can increase IB, for example. Well, we have fixed it, giving it the minimum value so that it doesn't meet, right? Just like we are fixing, if we can fix W or L of 6, assuming we meet the minimum value of VD sat, right? We have not put any other constraints. So in reality, you may have to, so this is just a first cut design, right? You want to make sure you meet everything, and then at least for the first cut design, you need to go back and make some certain checks. Okay, so you can get W over L 5 and 8. What else is left? So W over L 3, 4. For now we'll assume that it's the same VD sat 0.5. Okay, you'll have to go back to the input common mode range and find out. For now we'll assume that it's the same VD sat. So this will give you some values. Let me give you the okay, if this is the case, this is 4, this is 16, this will give you 4 again. Yes. Yes. Okay, we are going to come to that. We have not even come there yet, right? Obviously, yes. So in reality, okay, we'll come to that. Okay, we'll come to that changing the sync part. We have not even come there yet. Okay. What else is left actually? So we have done unity gain, peak to peak, phase margin, slew rate. So what is left is DC gain. What is DC gain going to give you? The length of the devices, right? So if you see, each one of these specs actually decides a particular parameter, right? A particular design parameter of your op amp. Okay. Phase margin sets CC. Slew rate sets IA and IB, the bias currents. FU sets WRF 1. The output swing sets WRL of the others. DC gain sets the else. Right? This is the fourth one, fifth one. Sorry? Yeah, we'll go back and check. Okay, first let's do a first cut design. Then we'll go back to the checks after this. What is this? What is the DC gain? Okay, so spec is 10,000. What is it in terms of the parameters? correct? So I'm going to call this A1 and A2. Okay? So now, do you know GM1? We do. Do you know GM6? We do. Right? Do you know GDS2, GDS4? We don't. But we can write it in terms of lambda. Correct? What you can do is, you can write this in terms of W over L, K prime, Kn prime, Kn prime W over L, right? Times I. And then you'll get, this will be root of correct? This is going to be correct? Oh, sorry. It's lambda I. GDS is nothing but lambda I. Right? So now, you know everything else except for the lambdas. So you can write this as, you will get, let me see. You can do the same thing for the output stage also. Okay? Now you have got your gain and DC gain in terms of lambdas. You need to design the lambda. You need to design the length for a particular lambda which will give you this particular gain. Now last time when we did the folded cascode, the telescopic, we actually did it a different way. Right? We put in values of found out RDS and put in assumed L-min and so on. Correct? And we actually got RDS of the P was very different from RDS of the N. We'll go the opposite way here. Okay? We'll do it slightly differently. We'll put the constraint that all 4 lambdas are equal. Okay? If you say all 4 lambdas are equal, this will end up being by 4 lambda squared. Okay? And you can say this is 10,000. So what do you do? What do you get from this? You get lambda. What do you get from lambda? You know lambda L is a constant. So you find out L from lambda. Okay? You get something like 2.5 into 10 power minus 2. I want you to go back and, redo this design example by yourself. Right? That is the only way you will ever be able to, absorb everything. Right? Because in class I'm not doing the algebra. I'm basically stepping across and I'm giving you the answers. I want you to go back, sit down without looking at the notes, follow the steps. Right? Follow the steps independent of the notes. And then see what you get. Okay? Anybody else has a class now? Next hour? You have a class. Okay, then in that case we'll stop here because it's already quite late. We'll continue in tomorrow's class. There's just a little bit left.